Okay, just a few more topics this week, getting us used to equilibrium problems again, and then also taking a couple extra steps to look at the thermodynamics that led to the equilibrium expressions that we're so used to from general chemistry. I mentioned last time I was going to talk about and give you a homework assignment associated with the Le Chatelier's principle application to temperature type analyses that we enact in general chemistry. And so you're going to do that. I'm going to do it for one of the cases though, just to kind of give you a benchmark with how you would approach this problem from the standpoint of now analyzing one of these equations that deal with the temperature dependence of K. The easiest way to do this is to pick the equation that does have a constant delta H naught. Some of these arguments kind of go out the window depending on the functional form of the temperature dependence of delta H naught. But if it's constant, we know that this is applicable, and then so you're allowed to assume that it's constant too when you do this same sort of analysis for homework. What I've done is I've taken this expression and I've arranged it in a way where I'm solving for K at T2. And what we see is that we have K of T1 and then it's multiplied by this exponential. So there's a couple different cases to consider. Like I said, I'm going to consider some of the cases here together, and then you're going to do the other cases yourself. So what I'm going to say is let's assume that we do some analysis and that we have an endothermic reaction. And your homework will be doing this for an exothermic reaction. There are two things that happen to K. Okay, so here's the thing. If you change the temperature, you're changing the thermodynamics. So if you're changing the thermodynamics, you're going to shift that equilibrium. Okay, so how that equilibrium shifts, whether K gets bigger or smaller, and whether you get more or less products, it depends on, right, the sign of your delta H and whether you're raising or lowering temperature. So, like I said, just kind of keep that all in mind. Let's take an endothermic process. Then we know that delta H naught is positive. So then here are some things we can look at. Let's raise the temperature. So if we raise the temperature and T2 is greater than T1, right? If we raise the temperature and T2 is greater than T1, right? If I come and I look here, right? What I have is this subtraction here, where 1 over T2 is smaller than 1 over T1. So this term right here, right? Let me just put it in green or underline it in green. This term right here, right? That I'm going to signify down here as our parenthetical term that's underlined, right? In this situation, T2 being greater than T1, right? What we'll get from here is a negative number, right? T2 being greater than T1, right? Delta H is positive, okay? So now let's look at the exponential. Delta H is positive, R is positive, and this is negative. The negative and the negative cancel each other out. And what you get is e to a positive number, all right, as this term right here. So what happens to K if T2 is greater than T1? For an endothermic process, all right, e to a positive number, that's a number that's going to be greater than 1. So our new K looks like our old K times a bigger number, a number that's bigger than 1. Our new K has gone up, all right? For an endothermic process, as you raise the temperature, K goes up, right? Now, what that means to us physically, what we would see in the context of our reaction is you get more products as you raise the temperature. And why does that make sense? Remember where the products are in K? They're in the numerator. So to make K bigger, you would need to make that numerator bigger. Now, that's how we learn it in general chemistry. We say for an endothermic process, energy is a reactant for an endothermic process. So if I add energy in the form of kinetic energy, all right, equilibrium is going to shift to make more products because it's like I'm adding a reactant. Now, all that should sound familiar, but now again, we see a mathematical justification for it. It's really analyzing an expression that looks like this, thinking about what happens to this exponential, And if this exponential produces a number greater than 1, then your new K at your higher temperature, it's actually going to be bigger. Okay? Let's do it for lowering the temperature. So let's say we have an endothermic delta H, and we lower the temperature. So in that case, lowering the temperature would require T2 to be less than T1, right? If we look at that green parenthetical term up there, that's underlined, right? 1 over T1 is now going to be 1 over a bigger number. So 1 over T2 is bigger than 1 over T1 because we're talking about inverses here, right? So this parenthetical term, right, this is now going to be positive, right? It's positive. We know delta H is positive. This is a bigger number minus a smaller, oh, it's positive now. So what does our exponential look like? Our exponential looks like e to the minus a number, all right? E to the minus a number, right, where all these numbers here, right, end up looking like a situation where we're going to get something that's less than 1, okay? So if I look and I analyze this situation now, if I look at my K at T2, my new K, it looks like my old K at my original temperature times a number less than 1. So what has happened? It has gone down, right? It's gone down. And we can see that from the mathematical analysis, right? Again, how we explain it in general chemistry. If it's an endothermic process, energy is a reactant. So if I lower the temperature, then I'm taking reactant away. So then which way does the equilibrium shift? It shifts to the reactant side, and thus K is lowered, right? All that kind of makes sense here. Remember where the products are? Products are in the numerator. So what we would see experimentally, right, to make K go down is a shift where you actually get more reactants, all right? You get less product. You actually saw this with borax, but now we see mathematically where it's coming from, right? So what you're going to do in homework is you're going to start analyzing this sort of thing in the exact same way, spelling it out in as much detail as possible for an exothermic delta H. So you do some analysis and you have an exothermic delta H. What happens for the exothermic process if you lower the temperature, and what happens for the exothermic process if you raise the temperature. You're going to give me an explanation just like I did in the context of this equation and also the Gen Chem explanation of what happens, energy being a reactant or product, and removing or adding energy based off temperature. Okay? So I thought I would just give you a kind of head start on how you would think about it and start that analysis process. All right. Next week, we're going to deal with doing more complicated calculations involving equilibrium because we're going to have a lot more sort of background by then. But I do want to mention now, all right, what happens if we're not at our standards? What happens for, let's take for instance, we have real gases. What changes about everything we've talked about? And if you go back to one of the assumptions that we made, all right, is in the development of our equilibrium constant, we invoked chemical potential that had this form, all right? And we said we could use this because we're talking about gases and we're talking about ideal gases, and that's what we derived when we did it for ideal gases, okay? Now, if you have real gases, if you remember from earlier in the semester, the whole point of then developing this and then associating it with fugacity is that fugacity was a stand-in for P over P naught. Okay? So if you have real gases, what you do is you go back and instead of using this expression, you go and you use this expression. Okay? Well, hold on a second. Nothing really then changes about any of the math except, right? Because remember, we kind of got rid of P naught. We didn't get rid of it, but we just called it 1 bar, okay? If you look here, right, essentially the only thing that changes is this P over P naught, right, is replaced with fugacity. Okay? We define fugacity to keep this exact same mathematical form, right? But then just kind of deal with the realness in this term. Remember where this ended up? This ended up in our Q and in our K. Right? Before we get to like what you actually do then. What about other substances? What about any other substance? Remember, anything we've talked about since then, right? We defined an activity. Okay? So we have a mu naught plus RT, the natural log, right, of activity. And for all other substances, okay, what we did is we said, I want to recreate this natural form of a mu naught, an RT, and a natural log, right? And I'm going to define activity in a way where this mathematical form is kept. Well, if you look at our derivation, and we're dealing with substances like solids, liquids, aqueous species, right? What changes about that analysis? Well, it looks like the exact same mathematical form, except instead of pressures there, what do you have? You have activities, right? So everything that we talked about, right? Everything that we talked about where we ended up with a pressure that we were analyzing, all we have to do is we have to keep the exact same analysis. But when we go to think about what K and Q look like, instead of using a pressure, if it's a real gas, we use fugacity. If it's another substance, right, we don't use pressure, we don't use concentration, okay, we use activity, right? And that's just a main, really important, critical idea, and it's why we define chemical potential the way we have. Because nothing changes about our analysis except the behavior away from our standards, from our ideal situations, right? It now manifests in using appropriate other terms in place of concentrations or pressures, okay? Instead of using concentrations or pressures, you use fugacities for real pressures, for real gas behaviors, and you use activities for everything else, right? And that's the benefit of keeping that mathematical form. So we haven't really talked about Kc yet, right? And Kp and Kc, they relate to each other, right? Kp, for example, pressure of a product gas raised to its stoichiometric coefficient, pressure of a reactant gas raised to its stoichiometric coefficient over, pressure of product gas raised to its stoichiometric coefficient, other product raised to its stoichiometric coefficient, reactant raised to its stoichiometric coefficient, reactant raised to its stoichiometric coefficient, okay? This is only valid for ideal behavior. If any, or let's just take the example, all of these gases that are going into this Kp, if any of them involve non-ideal behavior, then we use the exact same thought process, the exact same math, except here in place of pressure, we put fugacity. And remember what fugacity is, it's like this experimental fitting. It has pressure inside it, but it also has corrections for non-ideality. Right? Fugacity of C, raised to its stoichiometric coefficient. So fugacity of D raised to its stoichiometric coefficient, fugacity of C raised to its stoichiometric coefficient, right? Fugacity of A raised to its stoichiometric coefficient, fugacity of B raised to its stoichiometric coefficient. It's the exact same setup, it's the exact same math. We're now using fugacities that are the activities of gases. All right, something from general chemistry. We have Kc. That's like concentration of a product raised to its stoichiometric coefficient, and concentration of another product raised to its stoichiometric coefficient, and concentration of reactants raised to their stoichiometric coefficient, and concentration of another reactant raised to that stoichiometric coefficient. This is true when everything is following whatever standard you're talking about. Now, whatever that means, and we don't have time to talk about it, whatever that means, concentrations are good when they're following a standard. Just like pressures are good when everything's ideal and you get this expression, but when there's realness, okay, I have to replace it with fugacities, right? Concentrations are the same thing. We'll just talk about it more next week, not in a ton of detail, but there's some standard where, yep, concentrations work out perfectly. But you wander out of that standard, and guess what you need to do? Real equilibrium problems involve not using concentrations for aqueous environments, but activities. And then you go and you find a way to experimentally or theoretically determine how concentration and activity relate to each other so that you can account for that non-ideal behavior or that behavior away from our standards. So the problems we do mathematically this week, all right, they all involve, right, pressures and concentrations, and we don't put much more thought into it. But we have to realize, based off of everything that we've talked about, all right, that once you wander away from standards, we kept the mathematical forms the same. We get similar expressions for Ks, but instead of using, all right, pressures for gases, we should be using fugacities. And instead of using concentrations, all right, for KCs and equilibrium problems involving KC, right, we should be using activities. And here you also see something that I referenced earlier, why we say fugacities are the activities of gases, because they do the same thing, right, that activities do for concentrations, right? So here's where I'll leave you with. One of the things we do with equilibrium problems on a Gen Chem level is we say, all right, when we see a solid or liquid, what do? You take your K expression that you have and you replace their concentrations with 1, right? We use unity. So we say they don't really have a concentration. You go ahead and whenever you're using them in a calculation, oh yeah, solid or liquid, we even like X them out in an ICE table, right? We say, oh, let's just replace that with a 1. What's actually happening is, all right, the reason they're replaced with a 1 is because for most solids and liquids, their activities are equal to 1. It's not that they don't have a concentration. It's just that when you actually look at their chemical behavior, all right, they won't influence equilibrium because the activity, which is the actual thing that matters for equilibrium problems, the activity is 1. So we just kind of put a 1 in there, and then their influence leaves the mathematics, right? We can actually derive a formula, though, for activity. And we can look for situations where it won't be 1 for a solid or for a solid or liquid. Okay? So hopefully by now you've remember that, yep, I just put these with 1 in my equilibrium expressions. Whenever I'm using an ICE table, I just X them out. Let's justify that. And here's how we do it. What we do is we start, as we have a lot in these videos, with a natural variable relationship. Okay? So let's derive this formula. We start with, right, partial G, partial P, done at a constant T, is equal to V. This is where we start with. Now, the reason we start here is because what we end up doing is we end up saying, okay, experimentally, how do we get these activities for solids and liquids to matter? And it turns out that we have to have extreme changes in pressure. So that's why this is our starting point. because it ends up being pressure as like the main thing that could possibly move this away from 1. But we'll also see that when we analyze this, when we're close to standard conditions, when we're close to typical atmospheric conditions, the activity is 1. But like I said, we're going to justify that. Let's divide both sides by n. This becomes d mu dp done at a constant t. Looks like molar volume. All right. Let's go ahead then and let's substitute in for mu. Now, what we know is for any species, like a solid or liquid, we can do some work and we can do some math. And I'm going to write this over the right-hand side so you can write there in your notes. And we know that for mu can be expressed as mu naught plus RT, the natural log of A. And what we're trying to do is we're trying to solve for A, and we're seeing how A changes as pressure changes, right? It's all about activity now, because that's what we want to actually analyze. So we're going to substitute this in here, okay? So as we do that substitution, we're going to have d mu naught plus RT, natural log of A, dP, done at a constant T, looks like molar volume. We do that substitution. Now on the left-hand side, we can do the derivative. Now mu naught's just a number, right? It's at standard conditions. So when I take the derivative with respect to pressure, nothing happens. It goes away, right? It goes to 0, I should say. Okay, it goes away. R and T are constant for this partial derivative, so they're brought out front. So what we get is RT partial natural log of A partial P done at a constant temperature is equal to the molar volume. All right. We can solve this first order differential equation. We're going to bring the RT to this side, and we're also going to bring the DP. So we're going to get D natural log of A equals V over RT, right? V over RT dP, right? And this is done, importantly, right, under isothermal conditions. All right, this is done under isothermal conditions. Well, what we can do now is we can integrate both sides. All right. So what I'm going to do is I'm going to make sense of my integration limits here, right? And I'm going to remember some things we know about activity. Activities have some sort of standard setting where they approach what we expect them to approach. And it turns out, and what I mean by that is, we looked at activities with concentrations. And for something like a Raoult's law standard, activities approach concentration in certain limits. Well, it turns out for these guys that, all right, the activity is 1, right? The activity is 1 when the pressure is 1 bar. And this will make sense actually when you see the result. And it kind of even should make a little bit of sense now. The activity is 1 when we're at 1 bar. Oh yeah, wait, I can even look up here. If my activity is 1, what do I get? Mu equals mu naught, right? And when is mu naught measured? It's measured at 1 bar. So actually, even right now, we can kind of look here and say, oh yeah, when my activity is 1, right? When my activity is 1, then what I'm going to get here, okay, is a pressure of 1. So I'm going to take this up to some pressure P, and I'm going to take this to some activity A, right? Now, because we changed, like our limits are actually the variables we want in our end, we're going to put some primes here. So this becomes an A prime, and this becomes like a P prime, right? But this is an integral we can do. This becomes natural log of A prime evaluated at A, and then minus the natural log of 1, which is 0. Over here, it's isothermal. So the R can come out and the T can come out, and because this is for solids and liquids, all right, V, right, is essentially constant. And this is an approximation that we're going to use. This molar volume is constant, all right? It's an approximation that we use that's actually pretty valid. To change size, to change molar volume with pressure, all right, you need to get like crazy pressures on something. Like if you have a solid, like a marker or a piece of chalk or anything, right? Pressure changes do not change the molar volume much at all. That only applies for solids and liquids, right? We know pressure changes change molar volumes of gases like readily. But for solids and liquids, that molar volume is pretty fixed, right? It's pretty set. So let's do this integration, right? On the left-hand side, I already kind of said what we would get. We're going to get the natural log of a out of our integration, and then we analyze it at a, and we're going to get natural log of a. Okay. Now I'm going to subtract the natural log evaluated at an activity of 1. On this side, my v over RT comes out front. And I'm going to have the integral dp evaluated from p and 1. Oh, so it looks like p minus 1. The natural log of 1 is 0. And so we end up with this expression that we'll be able to analyze for solids and liquids whenever we need to discuss their activities. And again, why this works for solids and liquids is we just use that definition of activity and we applied that this molar volume would be constant. Right. So then, let's take this and let's analyze it. If our pressure is 1, what do we get on this side? We get that the natural log of A is 0. And so what does that tell you about A? A is 1, right? That's good to know, and that's good to get. That's good to recover. Because our activities of, so look at this. So if I'm at 1 bar of pressure, outside pressure, my activity is 1, right? And what are we trying to prove here? We're trying to prove that for solids and liquids, all right? It's a good approximation to say under most experimental situations, the activity is 1. Well, for sure at 1 bar, the activity is 1, okay? So now, if you think about what has to happen here, right? You actually have to get pretty big pressures for this side to deviate very far away, all right, from 0, all right? So it turns out that this molar volume term keeps this small, except for extreme pressures. And so if I have the natural log of A equals a small number, how do I solve for A? I go A equals e to that small number. And what am I going to get? Well, e to a small number is pretty close to 1. Okay? Now, it has to do with these molar volumes, like I said, having some appreciable quantification that keeps this small, right? Just to drive this point home, right? There's an example in your book that's great, right? And it's example 26-12. And they look at calculating the activity for solid carbon at 1000 degrees Celsius. I think degrees Celsius or Kelvin. And 100 bar pressure. Now 100 bar, that's a lot of pressure, right? And what they do is they take the temperature, they throw it in there. They look up a molar volume for this substance, right? And they throw it in there. They now know that this is like 99 bar. They pay attention to units on this side. And what they get, even at 100 times standard pressure, right? What they get for this situation is an activity of 1.01. Okay? So this is an incredibly powerful tool. This is why in general chemistry we say, hey, for solids and liquids, just pretend the activities are 1. Analyzing this gives us the pathway to say, all right, this over here is generally small for solids and liquids. And because this whole entire term over here is small for solids and liquids, the activity ends up being close to 1. Right? We will need this next week when we actually approach equilibrium problems from the standpoint of what about the activity of all those species in there? How do we deal with those situations? This week is about kind of laying the framework for those more difficult problems that we're going to be doing next week, okay? But we need to know how to do the normal problems, and we need to know how to analyze these concepts, right? We need to know now where this is coming from. It's not just something I'm telling you. The activities of solids and liquids are one, like I do with my Gen Chem students. Now we know how to prove it. Okay? So digest as much as you can. Send me any questions that you have.